Traces will not be on there. Let's go in here, continue. Okay. So in wrapping up yesterday, and thank you so much for all the volunteers I know that are going to volunteer. When we've kind of studied three different types of functions, right? Linear, quadratic, and exponential. Who can tell me that, like, if I'm looking at a graph, how do I know that it's linear? How do I know it's quadratic? And how do I know it's exponential? Raise your hand if you know, if you're dying to answer. All right. Yes, ma'am, Miss Watson, tell me. On a graph, yeah. How do I know? Okay, so let's talk about that. Straight line going up and down. Is that linear? Would y'all agree that that's linear? That is vertically. Well, okay. So, I mean, y'all agree that this is a linear function? Okay, I actually would disagree. I would agree that it's linear, but okay, she's saying it should look like this because these are functions, right? And maybe something like that, and maybe even something like this. But why would this one not be a function? Because it's undefined. And remember when we do that vertical line test and we pass it through, how many times can it touch? Only once. And this is touching a whole bunch. So it's not a function. So this is going to be my counter example. It is linear, but not a function. So just kind of keep that in mind, all right? So from a graph, absolutely, it has the word line in it. It is a straight line. Anybody know how to tell a quadratic or exponential? Okay, so it's a U shape for that quadratic. There's a fancy name for that U shape because it could be a U shape, it could be an N shape. It is a parabola, good. And I know it's spelled like parabola, but it's actually parabola. Okay, good. Exponential. So if I do this one right here and I'm like, you know, kind of just going along and then whoop, right? Or I'm like right here and I like dropped whoop, like this, okay? So this one right here, this is growth. Exponential growth where it's like real slow, and then it just takes off. And then this one right here is where it's decay, you know, it like drastically drops and then it kind of gets a little more even, okay? Now from an equation, let me talk to Sophia. Can you share with me which one do you want to tackle? Just like looking at an equation, you know, linear, quadratic, or exponential, do you know? Okay, let me start you off with this one, linear. Give me like slope-intercept form. What's slope-intercept form? What is it? Y equals what? Y equals, it's been a while. Yay, mx plus b, right? So when you're looking at an equation, the basic thing is that the greatest exponent is what? What is the biggest exponent on x? Exponents, those little baby numbers that go on top, right? And if nothing is there, it must be a 1. Very good. So the greatest exponent is 1. If your greatest exponent is 1, ladies and gentlemen, then it is a linear equation, okay? All right, let me talk to Roman. Talk to me about quadratic. What is my greatest equation if it's a quadratic, sir? Or my greatest exponent, sorry about that.
2.
Yeah, it's 2, right? And since you're kind of on a roll, do you know, like, what is the standard form of a quadratic?
Oh my god, I know it has like a lot of letters. I forgot it.
Got a lot of letters. Anybody help them out? It's got an A. AX squared plus BX plus C equals 0. There you go. Yeah, it does have a lot of letters. All right. The exponential one is the one where the exponent is always, do you remember? You could look at your notes from yesterday, or no, the day before yesterday, right? Y'all remember this one, y equals a times b to the power of what? It's been 2 days. X. The exponent's got to be X. If it's exponential, X is the exponent or the variable, right? It's either X or it's T, right? That's another one that they like to use a lot. So like today, we're going to be talking about one where it looks like this. Y is equal to 8 times like 1 plus R to the power of T, that type of thing. Okay, we're going to be talking about those are exponential where you have that variable in your exponent. Okay. All right. Now from a table, and this is what we were talking about yesterday. Okay. Quinte, can you share with me, how do I know from a table? Do you know linear, quadratic, or exponential? Which one you want to tackle? Any of them? All right, let's do linear. That's the easiest one. So how do I know from a table if it's linear? Let's say I got like 1, 2, 3, 4. Okay. And I got like 5, 7, 9, and 11. How can I tell for sure that they are linear? That +2, right? Of course, that only works when you have a consistent even change over here, right? Which is +1. So basically, there's a couple of things here. Number one, you need to have a constant rate of change. Okay. And the other way you can look at it is if your first difference is the same. Okay. So my question now is going to be, what if I did this? What if I put like 6 and then 15? Did I just mess up the whole thing? Is it no longer linear? Because we're going up by 2 now and we're going up by 4. I didn't mess it up? Because why? Okay, so you got to divide it. Your change in y over the change in x, 2 over 1 reduces down to 2. And here you got the change in y over the change in x, so that's still going to be 4 over 2, which still 4 divided by 2 is 2. Everything reduces down to 2, a constant rate of change. Yes? Or you can always look at the first difference and see that it's the same. All right, let's talk about quadratic. Let's see. Navaya, do you remember about quadratic? Oh, she sent a message. Let's see, not really. Okay. Look at your notes from yesterday. Michaela, can you help her out? How can I tell about a quadratic? You don't remember? Let's look at this, okay? Now, go ahead. What were you going to say? I thought it is similar to linear, but it's not the first difference. It's the second difference. So let's say that I look at this. I got 5, 14, 29, and 15, right? So I got 5, 14, 29, and 15. And so if I'm looking at that difference, I know on my x, everything's going up by 1, right? +1. Over here, that's going to go up by what, 9? And that goes up by 15. And this one's 21. And I'm like, well, that first difference is not the same, right? But my numbers aren't getting like crazy big or anything. Like when it gets like crazy big or crazy small, then I know we're probably dealing with exponential. But right here, I'm going to go ahead and keep going to my second difference. That's +6. And then guess what? This is also +6, right? So when that second difference is the same, then you know it's quadratic, okay? There's also one other way that you can tell too. And like if you look at my little calculator right here, and you look at the numbers right here, does anybody see a pattern? Let me make it more obvious. Anybody see a pattern right here? Now they could be mean and give you a table that looks like mine, right? But if they're nice and they give you a table that looks like this, what do y'all see in there? Okay. It starts with the letter S and it has to do with that pattern. Jessica, do you know Jessica M? No? All right, I'm hearing the word being said. It's called symmetry. Yes, symmetry. And that's where you got that whole 5, 5, 14, 14, right? And I don't even have to click up. We would know that that next number is probably what? 29, because you just right there, right? Good. What do you do if you add another set of numbers like we did on the linear table? Aha, okay, well, you know what? On that one with the quadratic, you really do have to make sure that it's just going up by the same. That's a good question, ma'am. Okay, I would definitely just make sure that it's going up by the same. I might use the technique of putting in the calculator like we did yesterday and kind of plot one. You know, we had y equals and you go up to plot one, and you can see, you know, the numbers from your table on the graph. Okay. All right, good question. Exponential. Let's see, Javi, can you share with me on the table? How do I know, looking at a table, if I got exponential, sir? All right, I'm gonna give you a hint, okay? Oh, that's right, you weren't here yesterday, right? Okay, so I want you to look for a pattern here, okay? What do you see as the pattern, sir? Okay, it's going up by 5, it's going up by 10, then it's going up by 20. And you think I can get like a second difference out of that too? Okay, let's try. So if I got 5, we're gonna pretend that's a 5. 20 and a 40. And then I go, okay, that's up by 5. Okay, that's up by 10. Okay, that's up by 20. And then I want to do it again, right? And in between these two, I got 5. And in between these two, I got 10. Is that looking like it's quadratic? No, because my second difference is different, right? So that second difference is not the same. So that's not quadratic. So do you see another pattern? Or you want a lifeline? Yes. We're going to multiply by 2. So here's the deal. Anytime you multiply or divide, if you multiply or divide by the same number, it's exponential. Make sense? And so that's our crazy little wrap up from yesterday, okay? That's basically all the ways, the different representations, and how you can tell them apart, whether they give it to you in a graph, an equation, or finally a table, okay? Any questions on that, folks? All right, welcome, Alexis. All right, so let's go ahead. If y'all are okay with it, I want to go ahead and just real quick look at today's. And we're going to be looking at writing exponential equations, okay? So this is going back 2 days. Let me go ahead and make this a little bit bigger. And they're getting a little bit more detailed about it, right? So I want to point out one thing to you. If you look at this right here, where everything inside the parentheses right here, everything inside the parentheses is considered a growth factor, right? Last time we talked about, like, we had y equals a times b to the power of x, right? And we said, oh, okay, well, if b is greater than 1, then we know it's growth, right? And here they're kind of saying the same thing because they're adding 1 to it, right? And then here we know it's decay if b is less than 1, right? And that makes sense because we would be subtracting 1. So yet again, I just kind of want to point out these vocabulary terms. They talk about growth factor. That's the whole thing inside the parenthesis. And here you got a decay factor, and that's the whole thing inside that parenthesis. But they also have a term referring to your rate of decay, and that is just straight R. Okay? Here we have a rate of growth, and that is also just R, depending on the situation. Please note that they want it in decimal form, right? All right. So let's look at this first question. We have the original value of a painting is $9,000, and the value increases by 7% each year. Increases is also an important word. Because we know we're talking about increases, we're probably talking about what? Growth or decay? Growth, right? We probably should use this one. We want to write an exponential function to model this situation. So I'm going to show you. This tells me that we're talking about growth. This right here is probably my initial amount, A. And this right here is going to be my rate of growth. Now we got to make that into a decimal, right? So keep in mind when we have percentages, usually the percent looks bigger. You know, it looks bigger. Okay, than the decimal form. Now keep in mind we have 2 little O's in our percent sign, right? So that means we're going to start with our decimal here and move 2 times to the left. So we end up with 0.07. Make sense? Okay. 0.07. So I'm going to go ahead and write my equation. Y will equal my initial amount of 9,000 times 1 plus, because it's growth, 0.07 to the power of t, which, you know, we're going to be probably using x in there, okay? So just to let you know, if it's an answer choice on an exam, you're probably going to see it written like this. Y equals 9,000 times 1.07 to the power of t. Is everybody okay with where I get 1.07? I just added 1 plus this. Okay. And so this is probably the answer choice if it's a multiple choice test, what it would look like. Okay. Now they talk about finding the painting value in 15 years. I'm going to add a little s there. So who can tell me, let's see, Aaron, what variable is 15 years going to replace? Let me know if you need a hint. You said the y? The 1? The 1's not a variable? You got a choice here. You got a y and you got a t. The t, right? Because t is for time, and that makes sense because it's time, right? All right, so that is going to be that, and t is for time. So all we have to do, and you could use, you know, put it into y equals and look at your table, especially since t, you know, is a nice number. But I'm going to go ahead right here. Honestly, I'm just going to plug it in to the power of 15. So that's what's new, is that power of 15. So in your calculator, oh, I did say you may not need your calculator. I guess you do need your calculator. So I'll forgive you if you don't have it right away. But we're just going to type in 9,000, parenthesis, 1.07, close parenthesis, and then to put in the exponent, I have the caret. That's right below the clear, right? And then I put in 15, and then enter. And so we're talking about money. That means I like to usually include all my pennies, right? And when I do that, let me see. Oops. Okay. Right here. Come on up. Where is it? There we go. So I like to look at it right here, right? What do y'all think is it going to be? 0.28 or 0.29? 0.28. Yes, because 4 or less, let it rest. And they're talking about that number right here, right? 5 or more, raise the score. So keep that in mind. We're going to go ahead right here and write in the value is going to be in dollars, $24,831.28. Easy? Awesome. All right. Let's look at number 2. Okay. We have a sculpture is increasing in the value of a rate of 8%. So increasing rate of 8% per year, and its value in the year 2000 was 1,200. We want to write the exponential function to model this situation. So let me select. Who's the last person I spoke to? Oh, it was Aaron. Let me talk to Sophia. Today's your day, ma'am. Go ahead and share with me. If you don't feel comfortable just writing the whole equation, you kind of share with me what variables you think the different numbers could possibly be. Okay, increasing. Is that going to be growth or decay? Growth. I like that. Okay. And then this rate right here, what variable? Yeah. Let me zoom out so you can see the whole thing. Okay. Here we go. And we're looking at this rate one. So we're using y equals a times 1 plus r to the power of t. You know what? I should just write it down here. Y is equal to a times 1 plus r to the power of t. Okay, so now I can make it bigger again. And let's look at it right here. So this right here, what variable do you think that's going to be? R. And how do I rewrite it as a decimal?
You move the decimal 2 places to the left.
What happens? What does that make it?
Point. Why did I just forget that? 0.08.
There you go. Okay. So when we do this, we got R is equal to 0.08, right? And so in knowing this, Samantha, can you go ahead and write the equation for me? What am I looking at? Y equals what?
1,200.
Good. So you identify this as your initial amount. Good.
So I have a question.
Uh-huh.
Is the 1 required?
Is the what required?
The 1.
Yeah, that's a requirement because otherwise if it's a number less than 1, I'm thinking it's decay. Okay. So you got to have the 1.
0.08.
To the power of t. Okay, good. So now one thing I want to point out, this is our initial amount, right? What that makes it is it also makes this the initial year. So keep that in mind as we're addressing the next question, okay? So this one right here, of course, when we clean it up just a little bit, it's going to end up looking like this. Y is equal to 1,200. 1.08 to the power of t. Got it? All right, Aubrey, can you share with me, when I'm finding the sculpture's value in 2006, how do I interpret 2006? Yep, it's going to be about t. And what will t equal? Let me know if you need a hint. Yeah, because you take the 2000, right, and you subtract 2000 from 2006, and you get 6, right? Clinton's already got an answer. Let's see if he's right. So, Clinton, did you set it up like this? 1,200 times 1.08 to the power of 6?
Yes, ma'am. All
right, cool. So let's go ahead and let's see. We got 1,200. We got 1.08. And then we're going to put it to the power of 6. And he was absolutely correct. He had said that it was going to be 1904. Do you think he said 24 cents or 25 cents?
25.
Look at y'all able to round. That's good. All right. So we're looking at a value of, so it's probably dollars. And we got something like that, $1,904.25. Any questions? Super easy? Awesome. Let's go ahead. And I want to talk about, we're going to talk about decay, right? The key word here, decreasing, right? That tells me about decay. I want to do, let's see. You know what? I'm almost tempted to do this one here with you right here. Okay. Number 5. Oh, this is increasing. So if you have questions about this one, ask me. But yeah, I'm going to go ahead here with number 3. The population of the town is decreasing at a rate of 3% per year. So of course, you're going to use a little different equation, right? Y is equal to a times 1 minus r to the power of t, right? And in 2000, there were 1,700 people. We want to write the exponential function to model the situation. So right now, I'm going to pause the video. And right here, so really, really good with all the responses, guys. Right here, this is r. And you should have had 0.03 as your r. Did everybody move it enough? There might have been a couple people who didn't move it quite enough. Okay. Then, because we know we're just taking it 1, 2, right? So you got to have a 0.0. Okay. Now the other right here, this is our initial amount. That's A. We know it's decreasing, so that's minus, right? I'm going to go ahead and write it up. Y is equal to 1,700. 1 minus, that's kind of low for a minus, but you get it. And then to the power of t. We usually leave t in there whenever we're writing the equation. Just keep in mind, my favorite answer to this equation look a little bit like this. We got $1, take away 3 cents, that's 97 cents. Do y'all see why 1 minus 0.03 is 0.97? Okay, to the power of t. And then I got a couple people who told me, what is my value for t going to be in 2012? It's going to be 12. We subtract 2,000 and we get 12. So I'm just going to go ahead and put that in. 1,700, 0.97 to the power of, or was it? Okay, let me see. 12. And we are talking about people, yes? So we're not talking about money. We're talking about people, which means that half a kid, that's not really half a kid, that's a whole person. So we're going to go ahead and say 1, is it 80 or 79? 1,180 people, y'all, because that's 5 or more. So we raise the score. And so that's 1,180 people. I'm rounding it because half a person is gross. Yes? Okay. I'm just playing with you, but yeah, you get the idea. Yes? All right. People, we don't round. Dollars, you can round to the penny, right? That makes sense. And then, kind of speaking of that kind of stuff as far as rounding and anything, does anybody have any questions on number 3? Okay, I want to just float down right here to number 5 because this one came up a lot with questions. You know how they say, like, okay, it says since 2005, the amount of money spent at restaurants in the United States has increased by 7% each year. In the year 2005, about $360 billion was spent at restaurants. So I had a lot of people who were trying to put 360 with like all these zeros right after it. Yes? Because I think it's what? It's 1,000, a million, a billion. There we go. All right. That's a lot of zeros. No. So my suggestion is that you go ahead and write your equation. It's growth, right? But leave it at 360, right? And then you can put in the 1 plus, you got the 0.07, right? Everybody's okay with me just skipping ahead to the power of t. Now, keep this in mind, but when you do this, please know that y is going to be your total, but it's going to be your total dollars in billion. In billions. Get it? So if it gave you 2.5, then you know that's 2.5 billion, not $2.5, right? So that would be my suggestion when you're dealing with something like that that has a whole lot of numbers. Any questions? Okay, guys, I'm going to go ahead here. All right, ladies and gentlemen, if you still have questions on this, please feel free to come into Sing Time, ask me any questions you have. Other than that, have a beautiful day. Take care. Wrap up my video.